for, let's say, k minus 1 states, and then we have to prove that it is true for k states. Now, what does that mean in this context? Now, what does convert? What's it doing? It takes a machine G, a GNFA, and it rips out one state, modifies the labels on the transition arrows, so that G dashed, the GNFA that has one state less, and then passes on that G dashed, this slightly smaller GNFA, to another call of convert. Okay, so convert of G within it recursion will have a call to convert of G dashed. Okay, so what we're trying to show is if convert G dashed works, it is equivalent, then convert of G also works. So let's try and show that. That's the inductive step. Okay. So we assume the claim is true. Now what claim is that? Well, here's your claim, right? So for any machine G, this convert of G is equivalent to the machine, right? And what does convert? Remember what convert G gives you? It gives you a regular expression. It gives you an R. And this claim is that R is true it is equivalent to G. Okay? And so we're now saying if it's true for G dashed, one slightly smaller, this whole thing will be true also for G. Okay? Let's say it again. Here's your claim. So for G dashed, one slightly smaller, you put a G dashed here, G dashed here, G dashed here. Okay, that's assumed to be true. You assume it's true. And if it's true, then this claim, this whole thing, will also be true for G, which is one state bigger. Right? That's induction. You go from a smaller case, one smaller to the next. So you go from k minus 1 to k. All right. I hope you follow that. Okay. So. We'll assume that it's true. This claim here is true for k minus 1 states, and then try to prove that it's true for k states. Well, how? All right, how to do this? Now we need to see if G. We're taking a G. Try to remember the big picture. We're taking let's say a rather large, with K large, G NFA, and we're knocking it down one state at a time, making it smaller and smaller. And eventually we'll get to a G that only has 2 states, and then we can output the required regular expression. That's the whole point. Okay? So we need to show that as we knock it down by one state each time, that these two machines are equivalent. The two machines are equivalent. In other words, they recognize the same language. That's what equivalence means between two machines, right? They do the same job. So they recognize the same language. All right? So let's try to show that. Okay, so assume, so here's your machine, here's your input string W, right? And let's say for this input string, this machine accepts it. Okay? So all the W's that belong to the language, then this machine accepts that language. Okay? That's, you know, done that before. Right. Let's see. So you'll end up in some path. Now it's G is a GNFA. So there'll be lots of branches. So just as long as one of the paths ends up in an accept state, well, it's a GNFA, so it ends up in the accept state. Okay. For this string W, then that means that the sequence, you know, if you follow that particular path through the state history, I guess, you know, like the tree, then that particular path that ends up in the accept state will have a sequence, you know, over time. It will have a sequence of states that it goes through in that path. Now the first one, obviously, the first state has to be the start state. Now if this G accepts the string W, it'll end up in the accept state. So it starts in this one, ends up in that one, with all these intermediate states in between. Okay, that's for G. All right. Now there are two cases that happen now. Now we're talking about G dashed, and we're trying to show that G and G dashed do the same job. They recognize the same language, and hence they're, as machines, they're equivalent. All right. Now two cases. Either G dashed. For this path from start to accept. Now it's possible. Now there are two possibilities. It's possible in this sequence of states, the successful path, if you like, that ends up in the accept state. It's possible that the Q rip, that state, may not be amongst this sequence of states that G dashed. Now, if we, I'm trying to figure this out. So you have a machine G dashed. It has one state less. Okay, and the state that's missing is Q rip. This one, this here. Now this is the sequence of states to get to the accept state for G, the slightly bigger one, right? The machine with one state more than G dashed. Now it's possible that your Q rip is not amongst this sequence of states to get to the accept state. All right. So that means let's have a look at G dash's sequence of states and compare it with G's, and we'll find they're effectively the same. So they recognize the same language. Now why is that? Now assume now that G dash's the state that's ripped out of G to give you G dashed. Assume, there's two possibilities. Assume that in the first case it's not amongst this sequence of Qs. Alright? Well, so you rip out Q dashed, you modify all the transition arrows, you use the union trick. Now your G dashed will have those modified regular expressions which are the labels on transition arrows. They will now have the unioned form of the labels. Now because amongst these Qs here, they do not include Q rip. So they're like when you go from transition from here to here and here to here and so on to finally here, each of those transitions will will contain, in the union label, the label that's unioned, there will be the old label. Okay, now that's the essential idea. The G dashes labels, the label will include a union with the old R, the regular expression from the old transition before the Q rip got ripped out, right? And so therefore this can still accept your G dash now will behave the same way as here, because when you modify these transitions here for G dashed, you still have the same path. You still have a path that will get you to accept, because of the unioning with the R, the regular expression that you had labeling that transition before you ripped out the Q rip. Okay, and that'll allow you still to transition to the end. In other words, G dashed will also accept anything that G accepts, and hence they're equivalent. They're doing the same job. Okay, so that's the first part. Now the other part is, what do you do when here's the sequence of states for G. What happens when Q rip is one of these? It's in this sequence. That's the second case, and talk about that in the next session. And then we will do our first example of this process, of two examples. So the second one will have to be for next board.